Next, lemma 14. In this lemma, we link the notion of adherent points to something that we already know, namely convergent sequences and their limits. And the lemma states this. Say we have a real number x and a subset. Okay, I should have written capital X here. Let me just change that. And a subset capital X of R. Then small x is an adherent point of capital X if and only if you can find a sequence an, all of whose terms an are coming from X, which converges to this point small x. Okay, so that means this is the necessary and sufficient condition in terms of convergent sequences for a real number to be an adherent point of a set. So let's see the proof. Actually, this proof is one of the exercises, but let's do it now itself. So we start off the proof by assuming that X is an adherent point of X and produce one such sequence, and then we have to prove the converse. So let X be an adherent point of X. In other words, let X belong to the closure of X. Then for each positive integer n, this set is non-empty. The set of all elements y in X such that the distance of y from X is less than or equal to 1 over n. This set is non-empty. But why? Let's see. So X is an adherent point of X, but what does that mean? It means that for any epsilon greater than 0, we are able to find an element y in X that is epsilon close to small x. So here in place of epsilon we have 1 over n. So that means at least one such y is there, and that's why this set is non-empty. Okay, so this is the reason. So now we are looking at a family or a collection of sets indexed by the positive integers, and all these sets are non-empty. So this is a situation where we can use the axiom of choice. So by the axiom of choice, there exists a sequence yn. If you want, you can call it an because that is there in the statement, but let me just call it yn. It does not matter what we call it, such that yn belongs to this set. For each positive integer n. And you recall why we are getting a sequence yn. That's because the family of sets we have here is indexed by the positive integers, and that's why. Okay, by the way, what does the axiom of choice actually states? It actually states that the Cartesian product of these sets is itself a non-empty set. So that means there is an element which will be a tuple in that Cartesian product. Now since the product is indexed by, or rather the family is indexed by positive integers, so that's why we are getting a sequence. Okay, that is the tuple, and you can see that here I have taken n to be a positive integer. N varies over all the positive integers because that is the index set. Okay, so now, so this happens for each positive integer n, and we can still write something else in place of this. In other words, for each positive integer n, first of all yn belongs to x. Okay, and the second thing is that the distance between yn and x is less than or equal to 1 over n. So that means the sequence yn that you have here is actually a sequence in x, because all the terms are coming from x, and that's what we wanted for that sequence an. And these inequalities would imply that the limit of yn exists and is equal to x. Exactly how, that I am leaving to you. Having seen so many things, you should be able to at least prove that these inequalities imply that the limit of yn exists and is equal to x. Thus, this is a sequence in x, and by sequence in x I of course mean that all the yns belong to x, that converges to small x. So this is one half of the proof. Now conversely, let Zn, here if you want you can make n vary from 0 to infinity, but I am just simply taking n from 1. And you also know that it does not really matter where we start n, because you can relabel a sequence and make the index start from any integer, actually even negative integers also. Nothing essentially changes, only the way you write the terms that changes. Okay, so conversely, let this be a sequence in x that converges to small x. So now our aim is to prove that small x is actually an adherent point of capital X. Now it's not given that small x belongs to the closure of x. That's what we want to prove now. It is now given that there is a sequence Zn, all of whose elements are coming from capital X, and that converges to small x. So this should imply that small x is an adherent point. Then simply from the convergence of Zn to x, we have this epsilon greater than 0, there exists a positive integer n such that the distance between Zn and x does not exceed epsilon for all positive integers small n greater than or equal to capital N. So this is just simply the definition of convergence, that's it, nothing else. In particular, the distance between Z capital N, because these inequalities are starting at capital N, right? So at that stage, when small n is capital N, also it is true. And additionally, alongside, note that this belongs to X. Obviously this belongs to X, all the Zn belong to X, so in particular this also belongs to X. So what have we managed to show? We have shown that for any epsilon greater than 0, there is an element in X that is epsilon close to small x. So that simply says that small x is an adherent point of capital X. That is, it belongs to the closure of X. So that completes the proof. So this new notion of adherent points has now been linked to the previous notion of convergent sequences. So now when we think of adherent points, we can always use this equivalence and apply whatever result we know about convergent sequences to adherent points. Usually that's how mathematics goes, it moves forward. It's not that you find something new and that has nothing to do with whatever you already know, what comes before that new thing. Usually there is some link, and that's why maths works also. Now based on this notion of the closure of a set, we next define the notion of closed sets. Just for a moment, let's recall the notion of the closure of a set. You have a subset E of R, and you know what adherent points mean of E. Okay, so say X is a real number. Very loosely, if I say like this, X is an adherent point of E if X is very close to E. That's it. And the set of all adherent points is by definition the closure of E. And we have already seen that the points in E also are adherent points of E, and that's why E closure contains E inside of it. So this prompts a thought that what about this special case in which E is equal to E closure? That must give us something, no? So the next definition is about this case. So this is definition 15. Let E be a subset of R. We say that E is closed or is a closed subset if E is equal to its own closure. Now since we already have this fact this relation for any set E, that means this is true if and only if this is true. Do you see how? If say you assume that this containment is true, then using this one, which is always there, you get equality. And conversely, if you have equality, then of course you also have this containment. That means that a set E is closed, which by definition is this, if and only if E contains its closure, which in turn means that a set is closed if and only if the set contains all of its adherent points. So that's the next thing we are going to write here. In other words, E is closed if and only if you want to if you want to save space and time, I said if you want to space, no? You can write IWF, okay, for if and only if. E contains all of its adherent points. Now we can of course immediately say about the closedness or lack of it for some sets whose closures we have already calculated. Some special sets, for example the intervals and the other known subsets of R. In some of the previous examples, we calculated these closures. So based on that calculation, we have this next example. And here we are going to refer to those things. Yeah, from lemma 9112. Okay. From lemma 9112, if A and B are two real numbers related to each other like that, then the intervals this closed interval, this closed half infinite interval, do not close this one, okay, because whatever discussions we are having now, everything is happening inside R, okay, not R star. Then this one are all closed. Also, R, which is this interval. See, that's why I said that do not put just simply because we are saying closed sets, you will be tempted to use the square brackets. Don't do that, okay, because we are inside R. We won't use this other infinite extended real numbers for now at least. this is closed. But the other intervals, for example, the open interval, the half open intervals, or the open half infinite intervals like this, these are not closed because their closures do not equal them. Are not. They are not closed. And from lemma, oh, so these are not examples, these were results, these were lemmas. Anyway, and from lemma 9113, we have also seen that these sets are closed because their closures also equal themselves. Okay. The set of all natural numbers, the set of all integers are, actually we have already mentioned that here, but both the lemmas mention this thing. In this lemma, we have been asked to calculate the closure of this, which turns out to be equal to itself. And here also in this lemma, we have just simply been asked the same thing, but R, that symbol has been mentioned. This is closed, and the empty set is also closed because it equals its own closure. R closed, but the set of rational numbers is not, because its closure is not Q but rather R. And now the equivalent condition that we proved today for a real number to be an adherent point of a set in terms of sequences can now be used to again redefine closed sets in a different manner, in an equivalent way. So that is this next corollary. So here closedness will be expressed in terms of sequences like this. Let X be a subset of R if X is closed and AN is a sequence. Well, it's a convergent, I have to mention that. It's a convergent sequence. Whose elements are coming from X. Then the limit of the sequence must also be in X, and conversely. Is a convergent sequence consisting entirely of elements in X, then the limit of AN must belong to X. Conversely, if the limit of every convergent sequence of elements of X belongs to X, then X is necessarily closed. Okay, so let us take a few moments to see what this means. So this corollary is saying that you have your set, no? X. So this is your X. And say it's given that X is closed. Then if you encounter a sequence of points that converges to something, and the sequence should be entirely inside X, all of its terms must come from X, then the limit must also actually be inside X. And conversely, if this is what happens with every sequence inside X, that is, whenever you consider a convergent sequence inside X, then its limit must be inside X. If that is true for every such sequence, then X must be closed. How is this corollary following from that lemma? Is it lemma or theorem? Yeah, it's lemma. It's actually quite easy. Suppose X is closed, okay, and now you have a sequence that is convergent, so it has some limit, this. You want to prove that that limit actually belongs to X. By that previous lemma, what is the consequence? What is the conclusion in this case for the limit of this sequence? The conclusion is that the limit is actually an adherent point of X. That is, the limit must belong to the closure of X. But since it's given that X is closed, X is equal to its closure, and that's why the limit must belong to X itself. And conversely, suppose that the limit of every convergent sequence inside X is also in X. But then that means what? That means that the closure of X is contained in X. Why though? That's because if you take any arbitrary point in the closure, then by that lemma, there is at least one sequence in X which is convergent and which converges to that point. But by our hypothesis, that point must then lie inside X. In other words, every adherent point of X is in X. So that's why X is closed. Okay, so that is how this is proved. It's so immediate and obvious that the proof has not, it's not there in the text, but you can see that it's almost obvious. And that's just it for tonight. So we will see what comes next after this, next Sunday. And our next upload is this coming Tuesday, and on Tuesday let's go back to group theory from Herstein. So see you on Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.